Sodium chlorate decomposes to form sodium chloride and oxygen gas. If 1.02 liters of oxygen gas are produced at STP, what mass of sodium chloride remains? So this is a stoichiometry problem. We have a reaction. We're trying to figure out, in this case, we have the number of the volume of one of the products right here, the oxygen gas. We're looking for the mass of the sodium chloride that remains, and so that's the other product. In any stoichiometry problem, the first step you always have is basically going to be simply write out and balance the equation. And so in this case right here, we have sodium chlorate, and so sodium is Na, chlorate is ClO3, and so if we take those guys right here, is that first want to look up and take a look at your sheet that shows your polyatomic ions, and that's going to tell you what the valence of chlorate is. And so let's look at that first. And a quick look at that sheet shows us that chlorate has a valence of -1, and so sodium also has a valence of +1, and so that balances out there. And so this is a decomposition reaction, and so this is going to decompose, just turn straight into our next two things, which is going to form sodium chloride, NaCl, and oxygen gas. So plus, and I'm going to shift it down here because I didn't put enough room here. So plus O2. Sodium chloride, sodium has a valence of +1. Chlorine has a valence of -1, and so that balances out. Now I've got to go ahead and balance the full equation, same as we have before here. I have 1 sodium on the left. I have 1 sodium on the right. That works out. 1 chlorine on the left, 1 chlorine on the right, 3 oxygens on the left, and 2 oxygens on the right. And so that means I'm going to have to put a 2 out here and a 3 out here to balance. But now I have 2 sodiums on the left, and so I got to put a 2 out here, and I have 2 chlorines on the left, and then that gives you 2 chlorines on the right. So we're balanced now. So 2 NaClO3 yields 2 NaCl plus 3O2. That's our first step. Write and balance the equation. Next step we want to do is we want to take a look at what we start with in this particular problem. And in this particular problem, we are told we have 1.02 liters of oxygen gas at STP. And so the amount we start with is 1.02 liters of oxygen gas. And so we're going to set up our table, same as what we have in the past. We want to cancel liters of oxygen. We want to go to, first step in any stoichiometry problem is to go to moles, once you start up your table here. And so in this case, we have to convert from moles to liters. Or liters to moles. Anytime you're going from liters to moles or moles to liters, you have to ask what are the temperature and pressure. In this case right here, it's at STP. When it's at STP, we know that 1 mole of a gas, any gas, doesn't matter what it is, has a volume of 22.4 liters. And so 22.4 liters in 1 mole. That sort of cancels that one out here. Our next step is going to go from moles of what we started with to moles of what we want. In this case right here, what mass of sodium chloride is the question. And so sodium chloride is our NaCl. And so we want to look at the mole ratio between these two. And we see that oxygen gas has a 3 out front of it. So that's its coefficient. Sodium chloride has a 2 out front of it. That's its coefficient. So we have a 2 to 3 mole ratio. And so far we have gone through and we have canceled out liters of oxygen. We've canceled out moles of oxygen. And now we've got to moles of sodium chloride. And so our last step is going to be to go from moles of sodium chloride. Woo, if I can fit that in there. We're going to go from moles of sodium chloride to grams of sodium chloride, which is what we're looking for next. And so to do that, you're going to have to get out your periodic table. And so if you go and look on your periodic table, and of course you'll need a calculator for this as well, this is sort of what we said before, is that we say that sodium, look at that, tells us that sodium has a mass of 22.99, so 22.99 plus the mass of chlorine, which is 35.45. And so you add those up and you end up getting 58.44. And so 58.44 would be our bit that goes in here. So let's see if I can fit that. 58.44. That's a decimal right there. So, and that's in grams in 1 mole. So that ends up canceling off our last bit here. Cancels off moles of sodium chloride. And now all we have to do is we simply have to basically do the math on this. And so we'd multiply across the top. So you'd say 1.02 times 1 times 2 times 58.44, and then on the bottom divided by 22.4 and divided by 3, And so in this case right here, we get a final answer of 1.77407. And the units here are going to be grams of NaCl. And so that's our answer here. Significant figure-wise, we're only really given one value to start with, which is this 1.02 liters. So it's 3 significant figures. So our final answer is simply 1.77 grams of sodium chloride, or produced in this case. That's basically how you go ahead setting up a basic gas stoichiometry problem at STP. So let's continue here and see what's coming up next. So another problem here. So 5 liters of hydrogen at STP is burned in oxygen. Question is, how many liters of water vapor are produced when the vapor is brought to standard conditions? So in this case right here is that we know that we start off with 5 liters of hydrogen. We're burning it in oxygen. And so we're asking about how many liters of water vapor is the question. So we do have a reaction here. We're going to have to convert. And so first thing we'll do is set up our equation. So we have hydrogen we're starting with here. So H2 plus, we're burning it in oxygen, so plus O2. And this is going to give us water vapor, so H2O. And so to balance this guy out is that we go ahead and we say we have 2 hydrogens on the left, 2 on the right. That works. 2 oxygens on the left, 1 on the right, so we have to put a 2 out front here, but that then doubles our number of hydrogens, and so we've got this guy right here. So 2H2 plus O2 yields 2H2O, and we're nice and balanced. So let's set this up. We are only told one thing in this problem, that's that we have 5 liters of hydrogen. And so since we have 5 liters of hydrogen, that's what we're going to start off with. And so 5 liters of H2, and we're going to set up our table same as we have before. We want to get rid of liters of H2. We want the first step on stoichiometry problems is go to moles. So we know moles of hydrogen gas. And so to find this, if we're converting from liters to moles, we have to look and say, what's the temperature and pressure? STP. And so since we're at STP, then we know we can use our trick that in 1 mole, there are 22.4 liters. And so we've got that down. We can continue our calculation here. We want to now go from moles of hydrogen into moles of what we want. And in this case right here, it asks us how many liters of water vapor. And so we want to go to moles of H2O. So we've got that here. So let's look at our calculation, our chemical equation. And so we see there are how many H2s? We've got 2 is our coefficient up there. And for water vapor is 2. So 2 to 2 mole ratio. It's going to make things easy. And so now we want to go from moles of H2O to liters of water vapor. Okay, so we have moles of H2O to liters of H2O. Well, in this case right here is that what are the conditions? Same question came up as we did before. And so originally our 5 liters of hydrogen were at STP, but what about afterwards? So how many liters of water vapor produced when the vapor is brought to standard conditions? So standard conditions tell us this is going to end up at STP too. And so since it's also going to end up at STP, we know that 1 mole is equal to 22.4 liters of water vapor. And so sure enough, as we've talked about before, our units are going to cancel. Liters of hydrogen cancel liters of hydrogen. Moles hydrogen cancel moles hydrogen. Moles water vapor, or water cancel moles water. And that leaves us only with liters of hydrogen left over. And so in this case right here, we're going to go up, we say 5 times 2 on top times 1 times 22.4. And let's see, divided by 22.4, and then divided by 2. And guess what you get? If you do that, you notice we have, there's a 22.4 on the bottom, there's a 22.4 on top, there are 2's out here. We're going to get the same thing as we started with. We end up, when we're done with this guy right here, simply getting 5 liters of water vapor. Seems a little odd, but if you think about it, it makes sense. There's a 1-to-1 mole ratio between our hydrogen and between our water vapor, which means that for every molecule of hydrogen we have, we'll have the same number of molecules of water vapor. Similarly, we know that these gases are both at STP, and that at STP, 1 mole of a gas, or any amount of a gas, has the same volume as that same number of molecules of a different gas. Remember, that's the whole idea of molar volume. That's Avogadro's law. It doesn't matter what gas you have, they'll always have the same number of particles in the same volume for the same conditions. These 2 gases are at the same conditions. They have the same number of moles because their mole ratio is a 1-to-1 mole ratio. And so if I start off with 5 liters of hydrogen, I'm going to end up with 5 liters of water vapor. Now, if I'd gone to oxygen, I wouldn't have ended up with 5 liters. because I don't have a 1-to-1 mole ratio of hydrogen to oxygen. I've got half as many oxygens as I do hydrogens here. But this just goes to show you sort of the power of Avogadro's law, is you can end up with a weird case like this where you start off with 5 liters of hydrogen and you get exactly 5 liters of water vapor afterwards if they're at the same conditions. But this is basically how you do the stoichiometry problem, and it sort of reinforces what we saw again, or saw before with Avogadro's law. So a 14.3 gram piece of potassium reacts with water to release hydrogen gas. This hydrogen gas collected over water is found to have a temperature of 25 degrees Celsius when the barometric pressure is 755 torr. What volume of hydrogen gas is produced? Same type of thing to start off with here is we're going to write out our chemical equation. We have potassium, metal, K, plus water, H2O. And it's going to release hydrogen gas. So we know hydrogen gas is one of the things that's going to be made here. If you recognize this, we have an element plus a compound. This is going to be a single displacement reaction. And so in this case right here is that this actually is going to end up being, so I'm doing this right here, this would be potassium hydroxide, KOH. Hydroxide is -1, potassium is +1, plus hydrogen gas is how this is actually going to split up in this case. Water usually breaks up, instead of just splitting up into hydrogen and oxygen, breaks up into hydrogen ions, or hydronium ions, what we'll call them later, and hydroxide ions. And so we're going to end up with this here. Don't worry about that for right now, though. All we're really interested in is just getting this equation balanced. And so we have 1K on the left side, 1K on the right side. We have 2 hydrogens that are on the left side and 3 on the right side, which we do not like. And so as a result of this, we're going to have to put at least a 2 in front of our KOH. We have to change this later, but that's going to give us 2 of these guys right here, 2 potassiums. It also means we're going to end up getting, let's see what we've got on this guy right here, because we have 2 potassiums on the left, we have 2 potassiums on the right. Right now we have 2 oxygens on the left, and so that means we have to put a 2 out here. So now we have 2 oxygens on the left and 2 oxygens on the right. Currently this gives us 4 hydrogens. We have 2 that are in the KOH, and so we'll need 2 more right here. So this should balance. So we have 2 potassiums on the left, 2 potassiums on the right. We have 4 H's on the left, and then 2 plus 2 gives us 4 on the right, 2 oxygens on the left, and 2 oxygens on the right. So this is balanced. So 2K plus 2H2O yields 2 KOH plus H2. So setting this up, same way that we had before here, is that we have a 14.3 gram piece of potassium. So we start off with 14.3 grams of potassium. Want to set up our table. First thing we want to do is convert from grams to moles. We don't have to worry about, in this case, worrying about whether it's STP or not, because we're just converting from grams to moles. This is just a good old-fashioned stoichiometry that we've done for a while here. So potassium is 39.10 for its mass, so 39.10. I've never given myself enough space here. And that's in grams in 1 mole. That gets us from moles of potassium. Next up we want to go from is from moles of potassium, which is what we started with, to moles of what we want. And it says what volume of hydrogen gas. And so we want to go to hydrogen here. And so we look at things and we say for potassium, has a 2 out front, so 2 potassiums. Hydrogen gas has a 1 out front, so this is a 1 to 2 mole ratio. Now we want to go from moles, this is what volume. We'd want to go from moles to liters, and we have to look at the conditions. 25 degrees C, 755 torr, not at STP. So we can't use 22.4, and so that means we just want to go ahead and start this off just by going ahead and figuring out what the number of moles is here, because we'll have to use that in our ideal gas law. So we say 14.3 grams times 1 divided by the 39.1 for the mass of that, and then divided by 2. And so we end up getting, in this case, that our we're going to end up getting 0.1829 moles of hydrogen gas. Okay? And so this is what we have here. Best enough if you don't round it. We sort of round it a little bit just to make it fit here. So now we want to basically go ahead and put it into our ideal gas law, PV equals nRT. And so, you know, PV equals nRT, ideal gas law. So pressure. So in this case here, we're told the barometric pressure is 755 torr. But we don't want to put that in just yet because it also tells us it's collected over water. And so we have to subtract off the water vapor pressure. And so if we go ahead and if you look at your water vapor pressure chart, we see that we're at 25 degrees Celsius and it has a vapor pressure of 23.7 torr, or millimeters of mercury, so 23.7, and so we want to take our 755 minus 23.7, and that gives us 731.3 is the volume that we will use here, so 731.3 torr times the volume, which is what we're looking for, equals N, which is the one we just found, 0.1829 moles, times R, 62.366, not 9, and then times the temperature, which would be, it's in Celsius right now, 25 degrees Celsius, so 273.15 plus 25 gives us 298.15 Kelvin. And so at this point, all we have to do is just simply solve for our volume. And so we'll divide both sides by 731.3. And so we'll take our original moles here, which was the 0.1829, and then times 62.36, then times the 298.15, divided by the one that's over there on the left, the 731.3. And doing so gives us a total volume of 4.6500 moles. Sorry, liters. My bad. And so from that right there, let's look at significant figures. We got 3 to start off with right here. We had, so that means this guy right here should technically have 1, 2, 3. And so that means this guy should have 3 significant figures right here. The 731.3, this is round to the nearest torr, nearest degree, to the ones place. So that one has 3. 62.36 is infinite. 298.15 has 3. So our answer should have 3 significant figures. So our final answer here is just 4.65 liters is going to be our volume of hydrogen gas that's produced in this case. So 14.3 grams of potassium reacts with water, in this case where water is not the limiting reagent, and produces 4.65 liters of hydrogen gas. So one more case here. This is an example. As I said, we didn't work limiting reagents. What if we do have to limiting reagents? Remember those from stoichiometry stuff? It actually works exactly the same way. There's no difference in the way that you work one out than you did the previous stoichiometry ones if you're doing a gas stoichiometry problem. So in this case, we have 0.23 moles of nitrogen gas reacted with 2.3 liters of hydrogen gas to produce gaseous ammonia. So sort of the same reaction we had a couple problems ago, just in reverse. If the temperature is 500 K, the pressure is 210 torr, how many liters of ammonia are produced? First step, let's write out the chemical equation. We have nitrogen gas, N2, plus hydrogen gas, H2, and we're doing this to create ammonia, which we said we simply had to remember the formula for. It's just NH3. To balance is that, remember we had to balance out those hydrogens, so we said we have 6 here, 3 here, so we now have 2 nitrogens on the left, 2 on the right, 6 hydrogens on the left, and 6 on the right, so we're good to go. So we have 0.23 moles of nitrogen gas react with 2.3 liters of hydrogen to produce gaseous ammonia. And so we don't know which one's going to limit the reaction. First step is figure out the limiting reagent. And so let's start off here by finding out which one's going to limit this. And so we start off with 0.23 moles of our nitrogen. We want to convert to what the units of the other one are, which are liters of hydrogen gas. And so we first have to go from, we have to cancel out moles of nitrogen. We want to go to moles of hydrogen, which is the one we're trying to see which one limits. We see that hydrogen has a coefficient of 3, nitrogen has a coefficient of 1 out there. And so when we do this, we're going to find that that we end up with basically 0.23 times 3, which should be 0.69 if I'm thinking correctly. Don't even get the calculator out that. Hope I did that right. So 0.69 moles of hydrogen gas. And so at this point, once we've got that, we see once again, is it going to fit with the 2.3 liters? Well, to convert to liters now, because of the fact that it's at 500 K and 210 torr, basically means that we're going to have to use our ideal gas law, PV equals nRT. We can't use our 22.4 here. And so we say that the pressure in this case is going to be, say 210 torr. times the volume, which is what we're looking for in this case, equals the number of moles, which is 0.69. 69. That is a 6 right there. And that's a 9. 69. Times 62.36 times the temperature, which is 500 Kelvin, right in there. Okay, so when we do this, is we're solving for volume, and so we're going to go ahead and multiply all that stuff that's over there on the right side. So 0.69 moles times 62.36 times 500 Kelvin, and then we're going to divide that by the 210 that's on the left, and we end up getting, in this case, that we have a volume here of, if I'm doing my math right, 102. Yeah, 102.44 liters for 4 liters of, in this case right here, is that we're talking about hydrogen gas. And so the question is, in order to react up our full 0.23 moles of nitrogen, we would need 102.4 liters of hydrogen. And we have how much? 2.3. So which one's going to run out first? Definitely the hydrogen, because we only have 2.3 liters of it here. And so basically, this is what we're going to start with here. We have 2.3 liters of hydrogen gas. That's going to be our limiting reagent right up here. And so all of our calculations are going to come off of that guy. And so from there, let's go ahead and set this up going forward. Is we want to figure out how many liters of ammonia is our question. And so to do this is that we start off with 2.3 liters of hydrogen gas, but because it's not at STP, we're going to have to go back through our PV equals nRT, our ideal gas law again. So we say the pressure in this case is 210, as we said before, times the volume. In this case, we know what the volume is. It's 2.3 liters of our hydrogen gas in this case, equals N, the number of moles, which we do not know. Remember the number of moles that we had over here is basically what happened if we used up the full 0.23, which is not true. We didn't use up that much. We didn't have enough, because we didn't have enough hydrogen available. So this guy is sort of gone as well. So number of moles, what we're looking for, times 62.36 times the temperature, which is 500 torr. 500 Kelvin. Torr is not a temperature. So solving this out here, we would take what's on the now on the left side, 210 times 2.3 liters, divide it by what's on the right, 62.36, and divided by 500 Kelvin. And so in this case right here, that we get that the number of moles of our hydrogen gas is simply 0.0, that's 0.01549 moles of H2. Now that we've got that, we're going to set up our table. So that's a 0, which looks like a D because apparently the screen is writing me off on the edge there. 0. Go ahead and erase that. I don't need that guy up there. There we are. So 0.01549 moles of H2. We want to set up our table across here. We want to go from moles of H2 into liters of ammonia. So first we want to go to moles of ammonia. NH3, sorry about that. And so we look up here and we say, how many moles of H2 do we have? We have 3 H2s. How many ammonias do we have? We have 2 ammonias sitting right up there. And so that gives us the moles of ammonia. We now want to go from moles of ammonia to liters of ammonia, but we can't do that because it's not at STP directly. We're going to have to do what we did before, go through PV equals nRT again. And I will tell you this is about as long of a problem as you're going to get here. So if you can handle this one, and that's the reason why I threw it up here, is to give you the most complex one I could think of, then you will be good on this. And so let's figure out what we equal here. And so we get out our calculators. Once again, we say that we have 0.01549 moles of ammonia times 2 divided by 3. And so in this case, I get that the amount of ammonia we have here is 0.01032.7 moles of ammonia in H3. But now we have to go back and plug it back into PV equals nRT. So the pressure is 210. The volume here we do not know. That's what we're looking for. Equals N, which we just found as 0.01032.7 times 62.36 times the temperature, which is 500 K. And we do this, once again, we're going to say that original number of moles over here on the right side times 62.36 times 500. Then we got divide both sides by 210. And so dividing that by 210, we end up getting a total final answer of 1.533, which in this case we have two significant figures going to be the ones to dominate here. And so we'll have 1.5 liters of ammonia, NH3. And that's our final answer. And so you can sort of see what we end up with here. As I said before, this is as complex as they get. You're never going to see one in this class that's any more complex than that. In fact, actually, you're not even going to see one that's this complex. But I just wanted to take you through an example of a limiting reagent problem and a very complex limiting reagent problem whenever you have a gas stoichiometry that's not at STP. Quite obviously, if this had been at STP, this would have been a much easier problem. We wouldn't have had to go through the ideal gas law 3 separate times. We could have just gone ahead and put our 22.4 in. But since we've got this 500K right here, we've got this 210 torr, we can't do that. And so this is sort of where we're stuck. So that's how you go about doing basic gas stoichiometry problems. And that finishes up this lesson.